This is the practice test walkthrough for chapters 15 to 17. The universe is always trending in the direction of disorder. The term for this is entropy. Okay, the universe always becomes more and more disordered, more chaotic. Anything that leads to more chaos and disorganization is likely to happen spontaneously, so answer choice B. Energy is blank during a chemical or physical change. Little typo there, I should say chemical or physical change. And the answer here is that energy is neither created nor destroyed. That's called the law of conservation of energy. That is also called the first law of thermodynamics. And actually the answer to number 1 is also known as the second law of thermodynamics, entropy. Number 3, which of the following factors will affect the rate of reaction? The nature of the reactants, concentration of the reactants, the temperature, or all of the above? The answer here is D, all of the above. The other factor that could affect it would be catalysts, and surface area would also affect the rate of reaction. Which of the following statements about catalysts is not true? A catalyst can initiate a reaction, catalyst can accelerate a reaction. A catalyst is not consumed during a reaction, or a catalyst decreases the activation energy for a reaction. Well, D, C, and B are all true about a catalyst, so the one that is not true is A. Catalysts do not initiate reactions. They can speed it up, they lower the activation energy, and they don't get used up, but they're not initiating a reaction. In this reaction, which of the following factors will increase the concentration of H2O? So we're looking for something that's going to shift the equilibrium toward the right. Increasing the pressure would actually shift it toward the left, because there are 6 moles of gas on the left and 7 on the right, so that would shift it left. Increasing catalyst would not have any effect on the equilibrium. Decreasing the pressure would be the same, would be the opposite of increasing, so that will shift it to the right. Shifting it to the right increases the concentration of H2O, which we would want. Increasing temperature, the heat is on the right, so increasing temperature will shift the whole thing to the left. The answer here is C. Decreasing the pressure will shift the equilibrium to the right, which will give us more H2O. A catalyst blanks the activation energy required for a reaction to take place. It lowers the activation energy, which makes more collisions get over the activation energy threshold, which speeds up the reaction. If the equilibrium constant is greater than, less than, plus, or equal to 1, it means that products are favored at equilibrium. Well, if the equilibrium constant is greater than 1, then the products are favored. In an exothermic reaction, which means heat is on the right-hand side of the reaction, equilibrium shifts blank when the temperature is lowered. So if heat is on the right, because it's exothermic, the temperature is lowered, that means removing something from the right-hand side, and removing something pulls to the same side, so if we're removing it from the right, it's going to shift to the right. In this reaction, 2H2 plus O2 produces 2H2O. Heat is evolved, which means heat is released. So heat is on the right-hand side with the water. What happens when the hydrogen is added to the equilibrium mixture at a constant volume? So we're adding something to the left-hand side, which means it's going to shift the equilibrium to the right. Now, which of the following things would happen if you shift the equilibrium to the right? Temperature increases. Well, if heat is on the right and we're shifting to the right, that means that the temperature, you're getting more heat, which means the temperature increases. All of the other things would be, well, temperature unaffected just isn't an option. More oxygen would be produced if we went to the left. Temperature would decrease if we went to the left. So we're going to the right in this case, so the only choice there is A. Temperature increases, you're producing more heat. According to Le Chatelier's principle, when the volume is increased, equilibrium shifts to the left in which of the following reversible reactions? So shifting to the left when the volume is increased. Volume increased is the same as pressure decreasing. So that means it's going to favor the side of the reaction which has more moles of gas. So we need to find and we want it to shift to the left. So we need to find a reaction which has more moles of gas on the left-hand side. In A, you've got 1 mole on the left and 2 on the right, so that's not it. In B, you've got 1 plus 1 on the left and you've got 2 on the right. There's no difference, so the pressure actually wouldn't affect it at all, or the volume. In C, you've got 1, 2 on the left and 1 on the right, so that's going to be the one we're looking for. Answer choice C would be the one that would shift to the left when you increase the volume, which is the same as decreasing the pressure. Are the following changes an increase or decrease in entropy? So we're looking for things becoming more or less disorganized or disordered. Carbon dioxide is dissolved in a sugar solution to make soda. Well, anytime you dissolve a gas, carbon dioxide gas, a gas into a liquid, it becomes less disordered, which is a decrease in entropy. Some things dissolving are increases, like if you dissolve salt in water, that's increasing entropy. But dissolving a gas in a liquid actually decreases the entropy. Ice melts to form liquid water. So we're going from a solid to a liquid. That is always going to be an increase in entropy because the molecules are starting to move around more, which gives them more disorder, more randomness. So it's increasing the entropy. Vinegar and baking soda react to produce carbon dioxide gas. So this time we have a reaction that produces a gas. You're starting with a liquid and a solid, and you're ending up with a gas plus some other stuff as well. But anytime you increase the amount of gas in a reaction, that's going to increase the entropy, increase the disorder. So we go from a liquid and a solid to a gas, on liquid and solid on the left, and one of the products on the right is a gas. That's an increase in entropy. Explain how increasing the surface area of one or more reactants can speed up the rate of a reaction. Be as specific as possible. Okay, so I'm going to just talk through this because it would be too long to write out on this video. So increasing the surface area, right, if you have a reactant that's made up of all these particles that are in a nice, neat solid, well, any reactant particles that are going to react with it can only collide with those particles that are around the outside edge. And in order for a reaction to happen, you need a collision. So I am not having a very fast reaction here because I'm only interacting the reactants that are circles with the reactants that are squares around the outside. If I take that same reactant, the square reactant, and I break it up into smaller and smaller pieces, now all of these particles can interact with the circles, right? Which means more collisions, which means more reaction happening faster. So anything that you can do to increase the number of collisions is going to increase the rate of reaction, and adding more surface area exposes more. This is the bottom line. Adding more surface area exposes more reactant to collisions. Increasing the number of collisions speeds up the reaction. Write the equilibrium constant expressions for the following equilibria. So we're doing the KEQ for these two reactions. So the first thing you need to look at, all of these are in the gas state, so they are all going to appear in the equilibrium expression. The reactants go on the bottom, so O3 times NO, that's the concentration of O3 times the concentration of NO becomes the denominator. The concentration of O2 times the concentration of NO2, those are the products, they go in the numerator. There are no coefficients on any of these substances, so there are no exponents anywhere in this expression. On the bottom, we have a solid, a gas, and a liquid. Well, solids do not get included in the equilibrium expression. Neither do liquids. So the only substance that's going to appear is the N2O, and since it's on the right-hand side, it's in the numerator. So it's N2O. If you want to put N2O over 1, that's fine. If you just left it as N2O with no denominator at all, that would also be correct. So it's simply the concentration of N2O. For this reaction, what is the equilibrium constant if the equilibrium concentrations are as follows? And we get the constants, the concentrations, the numbers there. So first, we need to set up the equilibrium expression. So KEQ, which is what we're going to be trying to find, is equal to the products go on the top. So PCl3, the concentration of PCl3 times the concentration of Cl2. They're both gases. They both get into the expression. No coefficients, which means no exponents. And then the reactant, there's only one, PCl5 goes on the bottom, no coefficient, so no exponent. So we're just going to multiply the concentrations of the two products and then divide by the concentration of the reactant, and that will give us KEQ. So now we plug in the numbers. For PCl3, we're given 0.0247 times, for chlorine, it's also 0.0247. And the concentration of the PCl5 is 0.0096. Now, if you notice, the concentration of the two products is the same. And that makes sense when you have a decomposition reaction, because you can't make one of these without making one of these. There's no coefficients. So the ratio is 1 to 1. So however much of this you make, you're going to make the same concentration, the same amount of that. So whenever you have a situation like this, the two things that are together like that should have equal concentrations, because you can't make one without the other, and you make the exact same amount of each. So anyway, to finish this off, we're going to do the math here. 0.0247 times 0.0247 and divided by 0.0096 becomes 0.0636, or in your calculator you might get 6.36 times 10 to the negative second, or 6.36 e negative 2. Okay, the equilibrium constant for this reaction is 8.75 times 10 to the negative second. So we're being given KEQ in this case, and we are given the concentration of the N2O4 of 1.72 times 10 to the negative second. We need to find the concentration of NO2. So first let's set up the expression, and then we can plug in the numbers. There's only one product, it's NO2. Now NO2 has a coefficient, it's got a coefficient of 2, so I'm going to square the concentration of NO2 in the expression, and then the denominator is N2O4, and there's no coefficient here, so no exponent in the expression. Now plug in the numbers I've got. I've got 0.0875, that's 875 times 10 to the negative 2, equals, I'm trying to find NO2, which in this case is squared, and I'm given 0.0172, which is 1.72 times 10 to the negative second. So now I have to solve. Okay, so it's 0.0875 times 0.0172 equals the NO2 squared. So what I get when I do that out is 0.001505 equals the concentration of NO2 squared. Now I have to get rid of that exponent, so I'm going to end up taking the square root of 0.001505. So the concentration of NO2 comes out to 0.0388, and the unit here is m for molarity. So that's the final answer you want up there. Okay, we've got another reaction. This is just the generic reaction, and this should have been, sorry, A, there should be an arrow. It should be A gas plus B gas, and then the arrow should be in the middle there, and then C on the right hand side. So we're given all the concentrations. We need to find the equilibrium constant. So to set it up, KEQ equals, the product is C, the reactants are A and B, and there are no coefficients in the equation, so there are no exponents in the expression. Plug in your numbers. We're given 0.30 over 0.45 times 0.63. Do out that math, and we end up with 1.06 as the equilibrium constant. That is the answer you're looking for. Lastly, oldies but goodies. This first one had a little bit of a gimme in it. That that coefficient shouldn't have been there, but that is the correct coefficient. So we need to finish balancing it. So 2CO2 is produced from CO and O2, so we just need to balance off. If we balance the carbons here, that gives us 2 carbons on the left and then 2 oxygens here and 2 oxygens here. Gives me 4 oxygens, and then on the right I've got 2 carbons, and 2 times O2 here is 4 oxygen. So that would be balancing it just by adding the 2 in that first spot. You don't need anything for the oxygen. What is the molarity if 4.59 grams of sodium chloride is added to water with a final volume of 175 milliliters? So remember, molarity equals moles per liter. Well, we're not given moles, we're given grams. So we have to convert from grams to moles, which is the mass divided by the molar mass. So we're given 4.59. The molar mass of sodium chloride is 58.4 grams per mole. So if we do that out, we get 0.0786 moles. Okay, so it's 0.0786 moles divided by, and we need liters, but we're given milliliters, so we move that decimal 1, 2, 3 places over. It's 0.175 liters. That's the molarity, and the molarity is going to be equal to 0.449 molar. There's your final answer there. So remember, you're going to need your to know how to write the equilibrium constant expression and how to solve it. You need to understand what happens when you do different things to a state of equilibrium, how it shifts, and what that means for the concentrations on both sides. You need to know what happens when you add something to one side, what happens when you take something away, what happens when you change the pressure and the volume, or what happens when you increase or decrease temperature. You also need to know all your vocabulary about reaction rates, what's a catalyst, how does a catalyst work, what affects reaction rates like pressure, temperature, surface area, nature of the reactants, concentration. Well, how do all those things change the reaction rate, and what is energy, what are the first and second laws of thermodynamics? You need to know that. And if you have all that together and you know how to solve those problems and do the questions on this test, then you should be in great shape. See you soon.